covalent bonding, understanding of the quantum theory of electron. Okay. You know, just saying that makes you sound bitsy. So if you go home and like, yeah, well, you know, in class we've been talking about bonding, covalent bonding, and how it relates to the quantum model of electron orbital mechanics. We'll be like, wow, that sounds very impressive. And then you'll be like, whatever. No big.
Are you trying to? Are you gonna like brag to someone about this?
Me? No.
Yeah.
Am I gonna brag? No. But I'm saying you can. But no, I think it's very fancy sounding. But we're gonna get to it because today we're gonna get to the point where I think it actually gets to be quite fun. I think so. Because we've learned so far how covalent compounds form by combining S and P orbitals to produce hybrid orbitals. And really quickly, remind me, what has to go in a hybrid orbital? Sigma bonds and lone pairs go in hybrid orbitals.
I almost said electrons. By the way, I almost said electrons.
Well, that's okay. That's fair.
Well, it makes sense.
Yeah, we're talking about electrons. That's cool. So, sigma bonds and lone pairs always go in hybrid orbitals. But today we're going to learn about why that is and what the three-dimensional geometry of covalent compounds is. Jonesy, how we doing?
We're good.
Good. All right. The basic shape of SP, D, and F orbitals. Now, I will say that these are all in like their simplest formations, and as you move to higher levels, they can get a little funkier than this. These are the basic shapes of SP, D, and F orbitals. Spherical, p orbitals are dumbbell shaped, d orbitals are double dumbbell shaped. I think people used to call me that. F orbitals are complicated. Okay, so
The F orbital is literally just called complex.
its shape is called complex. That's right.
That's interesting.
Okay, so these shapes are very efficient for holding electrons in lone atoms, and we know that do in fact work, but they don't describe the shape of molecular compounds. P orbitals exist at 90 degree or they're orthogonal to one another. They exist at 90 degree angles to one another. But there is a field of chemistry called Xray crystallography. It is really cool. This is how we know the shapes of molecules. I want you to know just random knowledge we claim to know. Though when I show you a picture of what Xray crystallography looks, it kind of seems like it's just voodoo magic. But when we do Xray crystal... we do X-ray crystallography, what we do is we shine above X-rays through a crystal of the compound we are interested in, and in doing so, it actually helps us draw an electron density map, and we can use that with a little bit of interpretation to determine the shape of a course in this once, and I'm not going to lie, I did not take a course in it, that's not true. A course that included an element of it, and I never quite got the grasp how that could tell me because here's the deal, that's wrong. Because actually, if I start here and go back to here, that could be 3/6 also be defined as 0 degrees. Exactly. You're not wrong.
He's wrong.
But it wasn't helpful to. So this is the furthest apart you can put 3 spokes from a wheel. All right? And when we do Sp2 hybridization, that's 3 spokes. That's 3 orbitals. So recall that Sp2 hybridization occurs when 1 s and 2 combine to form 3 new orbitals. Again, they're not 90 degrees. It's 120 degrees, which is a significant improvement over 90. And these orbitals are coplanar. They lie on the same plane. And there's a quick little thing to remember here that I find very helpful. S3 gives you a 3-dimensional shape, a tetrahedron. SP3, 3-dimensional. But SP2, well, these lie on the same plane. In fact, SP2 is 2-dimensional.
What about
It is, but, be quiet. Don't steal my thunder. Now you've stolen my thunder. Okay, so look here. Now, what I don't like about this diagram is that at least one of these bonds have to be what kind of bond?
double bond?
A double bond. Because you can only get Sp2 hybridization if there's at least one. What kind of bond? Very good. There's got to be, and I say at least one. That's not true. There has to be only one pi bond.
When are we going to have a formal chart? Formal chart.
Okay, so we can only get Sp2 hybridization if there's a bond present in the molecule. I'm going to make a note of that. I know it says it below. It's the same blank. It just spans a line. I changed my font. Now, again, just because, well, first of all, we should name this. What would we call this shape? What shape is it basically? I mean, we've got three things on there, and they form a triangle. And they all lie on planes. So how could we say that? It's triangular, and it sits flat on a plane.
Triangle.
I like it. Let's turn that into an adjective. You would think, but they go with trigonal, but that's okay, same idea. Trigonal.
This one also just bent.
Trigonal planar. Trigonal planar. And again, I don't like this diagram because what should this include? It's got to have a double bond, all right? Doesn't work if there's not a double bond. Oh boy, love that sound.